Okay, in this video, we're going to solve a binary integer program using the branch and bound algorithm. So here is our objective function, 2x1 plus x2 plus 3x3 plus 4x4, subject to this constraint, and subject to the constraint that all of the variables are either 0 or 1 or binary. So we're going to use the branch and bound algorithm. And so for the branch and bound algorithm, we're going to solve various LP relaxations of this problem. So we'll start by just solving the LP relaxation of this problem. And so I'll write this all to denote that kind of all of my variables are free to be whatever they want right now. And when I say we'll solve the LP relaxation, what I mean is that instead of xj being in 0 to 1, I'll relax this to say that just xj is between 0 and 1 for all j. And you can see how to, we could solve this using duality, but we could sort of just see how to solve this in this case. All of the variables, increasing them, contributes the same amount to sort of this left-hand side, and we need this left-hand side to be less than or equal to 7. And so we should look up at the objective function and see kind of which variable should we increase. And it's clear that we should increase the ones that have largest coefficient in front because they're giving us the most value in our objective function and sort of hurting us the same amount in this constraint. All the variables are acting the same in this constraint. So the LP relaxation solution for this thing is going to be, well, increase x4 as much as I can up to 1. I still have room to work with, so increase x3 as much as I want up to 1. I still have room to work with here, so increase x1. And then I can still increase x2, but not quite to 1, right? So I think the LP relaxation solution is going to be 1, 1 half, 1, 1. And this is going to give me a z value of 9 and a half. So 9 and 1 half here. Okay, and so now we're going to, this is not a feasible solution for a binary problem because this value is 1 half, right? It's not either 0 or 1, so we're going to have to branch here. So let's branch, and our two branches are going to be when I set, let's say, x1 equal to 0, and when I set x1 equal to 1. And now, under these two different restrictions, I can solve the LP relaxation. And I'll note that when x1 is 0, then I can, if I solve the LP relaxation, if x1 is 0, I can increase all of these variables up to their maximum, which is 1. So if x1 is equal to 0, then the solution to the LP relaxation is 0, 1, 1, 1. And we have z is 8. And this is a feasible solution. So this is our incumbent right now. This is our best feasible solution so far. Now, if x1 is equal to 1, well then x1 is equal to 1 in the LP relaxation of the whole thing. So we're going to get the same solution here. So we're going to get this 1, 1 half, 1, 1 as the solution to our LP relaxation. And so here we have an incumbent. So this side of the tree is done, but this side still is not a feasible solution. So we need to branch again. So let's branch again. We'll set x2 equal to 0 or x2 equal to 1. And now the same thing when I set x2 equal to 0 and I try to solve the LP relaxation, I can increase all of these variables as much as possible. And so the solution here is going to be 1, 0, 1, 1 for a z value of 9. So this z is going to be our new incumbent here. And if I set x2 equal to 1 and try to solve the LP relaxation, okay, so now if x2 is equal to 1, then I need 2 times x1 plus 2 times x3 plus 2 times x4 to be less than 5, less than or equal to 5. And using the same logic, okay, I want to increase x4 as much as possible up to 1, then there's still room. So increase x3 as much as possible up to 1, and then there's still room to work with. And now I can increase x1 to 1/2, right? So here, my solution to my LP relaxation here is going to be 1, 1/2, 1, 1. And this is going to give me a value of z, which is equal to 9.5. But we know that this is the value of my objective function in the end is going to be an integer, right? Because my variables are 0, 1 variables, and all of these coefficients are integers. So what it means is that, okay, the maximal value of the LP relaxation here is 9.5, and this means if I follow down this side of the tree, then the best possible solution I can get is going to be 9. It's going to be the floor of this thing, because it can be at most 9.5, but it has to be an integer, so I'll say that here z is going to be less than or equal to 9. And now our incumbent already has objective function value 9, so we don't have to follow this part of the tree anymore, because what this is saying is that if I follow down this tree, the best I can possibly do is z equals 9. And at this point, I've completed all of the subproblems, right? This was a feasible solution, so this side of the tree is completed. And now this is a feasible solution as well, so this side of the tree is completed. And so now this is my optimal solution. x1 equals 1, x2 equals 0, x3 equals 1, x4 equals 1.